So whether it be in science or just in day-to-day life, we typically measure things in one of two ways. We measure things either in mass by weighing it in grams or pounds, whatever, or by the amount of something, and chemistry is no exception. So let's go and think about oranges as an example. We measure them either by the pound or we measure by how many oranges we get in a bag. So for example, I know when I go to Kroger, I buy apples, not by the pound, but I buy them by the bag. And so I buy them based off of the amount or how many oranges there are. And chemical reactions, interestingly enough, occur between number of atoms, not masses. So what's more important for us to know is not necessarily the masses of the materials we're combining together, albeit it's an important thing, but rather we need to understand how the atoms interact with one another and how many atoms of each we have, because that helps us understand how much product we end up getting. Atoms are small, and a large number of atoms are present in a relatively small sample, so we need a number that is relatively large in order to take into account the number of atoms that are present in an amount of something. And you can think of a mole as like a counting number. A mole is a number that we use in chemistry. A mole is like a dozen of something, right? Regardless of what you have, a dozen of something is always 12, or a ream of paper. A ream of paper is always 500 pieces of paper. A chemist's counting number is the mole, which is equal to 6.02 times 10 to the 23rd atoms or molecules, and that is equivalent to a mole of something. This is a big number due to the fact that atoms and molecules are very, very small. They're very tiny, and so it makes it very difficult to deal with large quantities of materials because the number of atoms is relatively large. This number in and of itself is known as Avogadro's number, and because this is the number of atoms or molecules per mole, we can use this as a conversion factor between atoms, molecules, and moles. So we're going to use this as a conversion factor to be able to convert between different amounts of a substance. So the first thing it asks us here says to determine the number of atoms in 0.250 moles of sulfur. So we're going back to our dimensional analysis that we've learned previously, but we're just going to be utilizing different ways to convert between two things. And I'll tell you right now, there's only two ways we're going to do this. We're going to go either between grams and moles, or we're going to go between moles and atoms, or the combination of the two. So the amount of stuff you have to memorize and know how to do with dimensional analysis with this part is pretty straightforward. There's only really a couple of conversions you're going to end up having to do here, but the rules are exactly the same as what we've done previously. The first step is always to identify the given and identify the unknown. The given is moles and the unknown is atoms. So we're going to set this up just like what we've done previously. Start with your given, and then whatever unit is on top of the previous step ends up going on the bottom of the subsequent step. We then utilize the fact that we know that there are 6.02 times 10 to the 23rd atoms of sulfur in an individual mole and set up our equation just like this. Moles of sulfur will cancel, leaving us atoms of sulfur behind, and whatever we go through and punch into our calculator, we just need to keep in mind that we round that to 3 significant figures. Again, make sure that you understand and know how to work exponents in your calculator. If you need help with that, check my previous video over measurements to be able to help you and help guide you with that. All right, so I've got 2 practice problems here that we're going to go through here in just a moment. Take a moment yourself, work through them, and we'll be back in a moment. All right, so we're going to start this out the exact same way we've done all of our previous dimensional analysis problems. Identify what is given and what is unknown. We start with 1.7 moles of calcium, and we want to determine the number of atoms from that. So start with what's given, 1.7 moles of calcium. Whatever unit is on top of the first step has to go on the bottom of the next step. And just to give you a little hint with all of this, your mole number here, at least for this class, now again, other classes are going to differ, but for this class, our mole number is always 1. So it makes this a whole lot easier to go through and figure out. We can use Avogadro's number to go between moles and atoms, so 6.02 times 10 to the 23rd. I need a little more room to work with this than some of the other numbers that we've dealt with. But again, the idea is still the same. The mole numbers will cancel, and what we're left with is atoms. Just make sure that you include your exponent when you go through and write out your answer. So what I get a lot of people that will tell me when they go through and do this, they'll end up with a 1.0 when they round to correct significant figures. But you need to look at your calculator. You've got an exponent that's there. And then don't forget your chemical formula as well. So again, pretty straightforward here. Determine the number of moles found in 3.42 times 10 to the 22nd molecules of CaCl2. So again, we start from the beginning. It's the exact same style of problem. The only difference is we're starting with a different material than what we did previously. Molecules on the bottom. Again, we use Avogadro's number. Our mole number is 1. Now, I want you to be very aware that when you write these types of answers, you notice that you have an exponent on top of the first step and an exponent on the bottom of the previous step. You should not have an exponent that is massive here. You shouldn't end up with anything that's times 10 to the 45th, 46th, etc. What that means is that if you did that and you got that exponent, you probably typed it into your calculator incorrectly. So be very careful. Make sure you round to the appropriate number of significant figures. And there you go. So again, it's just a practice in math, but that is a very important conversion factor that we can use. And notice we can go between atoms and moles, molecules and moles. The atom number, the molecule number is always Avogadro's number. The mole number is always 1. So it makes it pretty easy to know where to put which individual part, which makes this a little bit easier than some of the stuff that we've gone through and done previously. So we've already gone through and talked a little bit about formula mass and the calculation of the mass of a mole of something. I told you I wanted you to start using grams per mole as the unit for when we do stuff off of the periodic table. I've used the term molar mass already. I'll just reiterate. It's the mass in grams of a substance that is equal to 1 mole and the formula mass. So each of the elements on the periodic table, the decimalized number there is how many grams there are in 1 mole of something. Notice that as we increase on the periodic table, the numbers for molar mass get larger, and that's due to the fact that each individual atom is getting bigger. Remember, 1 mole of something is the same number of atoms. It's like the difference in weight between a dozen chicken eggs and a dozen ostrich eggs. You may still have a dozen of each of them, but the ostrich eggs are going to have more mass because each individual ostrich egg is bigger than that of the chicken egg. And it's the same thing here. A mole of iron atoms is 55.85 grams, while a mole of phosphorus atoms is 30.97. Well, that's because each individual iron atom weighs more than that of phosphorus. Once again, we can utilize this as a conversion factor, this gram to mole thing, as a way to convert between two different substances, just like what we've done previously. So given the moles of the substance, we can use a conversion factor involving molar mass to go to grams of a substance. Remember the numbers on the previous slide are how many grams there are in 1 mole, just like what we discussed previously. The 1 always goes with the moles when we do these types of conversions. So let's continue our work with an example here. It says, how many grams are there in 0.45 moles of NaNO3? Well, again, just like what we do with any type of dimensional analysis problem, you identify the unknown, or in the given, and our given here is 0.45 moles of NaNO3, and our unknown is grams of NaNO3. So we do our dimensional analysis. Before then, though, we need the molar mass. We know we're going to be converting between grams and moles, so I need that number off of the periodic table. Molar mass of sodium is 22.99, molar mass of nitrogen is 14.01, and then 3 times 16 for your oxygens is 85 grams per mole. And now we set up our dimensional analysis just like what we've done previously. Start with the information in the problem, which is 0.45 moles of NaNO3. 1 mole goes on the bottom of the next step, and I can convert directly between moles and grams. And I make sure that I round to the appropriate number of significant figures. It should be 0.45 moles, not 45. But you get the idea here. So it's the same process. We're just going between grams and moles. So I know it's difficult to keep in mind all of these different types of conversions, but I think the big thing to remember is that the mole number is always 1. You follow the steps like what we do with dimensional analysis. Whatever unit's on top of the first step goes on the bottom of the next step, and that really helps guide you as you move through this. Now, the big thing here is that you have to be flexible when using these conversions. Know what you can and cannot convert between. If we want to go between moles and grams, we're going to utilize the molar mass. If we're going between atoms and molecules to moles, we use Avogadro's number. There may be more than one step that's involved, depending upon where we're starting and where we're trying to go. So it's very important to read the question carefully, know what you can and cannot do. You cannot convert directly between grams and atoms of something. That is a no-go. You have to go through moles first. There is no direct conversion between atoms and grams. Look on the right-hand side here. I created this. Yes, if you Google this, mine will be like the first or second that pops up. You can quote me on that. This is the mole wheel. The mole wheel is designed to help you understand what you can and cannot convert between. So the biggest thing here with the mole wheel is identify where you're starting and where you're going. So let's say I want to go between moles and grams. Well, notice that there's an arrow between moles and grams that says molar mass, so I'm going to use the molar mass that's found on the periodic table. If I want to go between moles and atoms, molecules, or particles, I'm going to utilize Avogadro's number. But notice that if I'm going between atoms, molecules, and particles, and I want to go to grams, I cannot do it directly. I have to go to moles first in order to do that, because you don't want to cut the mole in half, because the mole's going to have a really bad time. So that being said, you need to understand where we start and where we go. Now, you're not going to be given this on an exam, but this is a really nice tool to utilize in order to figure out where you're starting and where you're going. So I want us to calculate the mass of the following 9.96 times 10 to the 26th atoms of tellurium. All right, I'm going to do that here with you in just a moment. If you want, you can try it on your own. I'll tell you to go ahead and pause here if you wish, but I'm going to go through this with you here in just a minute. All right, so just like what we've done previously, identify what is given here. 9.96 times 10 to the 26th atoms of tellurium, and our unknown is mass. Remember, mass is grams. Start off with what's given. So 9.96 times 10 to the 26th atom. Whatever unit is on top of the first step has to go on the bottom of the next step. Now, using your mole wheel, remember, we're trying to get to grams. The only thing I can convert with atoms is moles. I cannot go directly between atoms and grams. We use Avogadro's number here. Now, we're not done, right? At the top of the step here, it says moles. We need to get grams, so we go another step. Now I can go between moles and grams. I just need to know the molar mass of tellurium. 127.60. Luckily, I have a giant periodic table that's next to me. I mean, like, massive in my house. Just tells you what kind of nerd I am. Okay? Again, when you do the math with this, take it one step at a time. You should not end up with any funky, massively large exponent with this. Okay? Make sure you round to 3 sig figs. So we're going to take 9.96 times 10 to the 26th. We're going to divide 6.02 times 10 to the 23rd. And multiply by 127.60. So we end up here is a large number, but not a ridiculously large number. So 211,000 grams of tellurium. So a lot of tellurium, but that's also a lot of atoms of tellurium, all right? So again, one step at a time. Read the question carefully. Know where you're starting, know where you're going. Make sure you can plug these into your calculator correctly. Let's do 2 more here. It says determine the number of moles in 45 grams of acetic acid. We want moles, we're given grams. So start off again with what's given. In order to do this, we need the molar mass here. So to get the molar mass of acetic acid, we're going to take 4 times 1.01 plus 2 times 12.01 plus 32, or 2 times 16. So 60.06 is our molar mass. All right, and then we just do our math here. So 45 divided by 60.06, round to 3 sig figs, so 0.750 moles of acetic acid. The last question here says determine the number of molecules in the same sample. So we can start with moles if we want to, because it is the same mole number from previous equation, but I want us to get into the habit of making sure we know where we start and where we're going from when we do these longer style problems. So I'm going to start with 45.0 grams of acetic acid again. I can only go from grams to moles, right? Cannot go directly between grams and molecules. So again, we're utilizing the molar mass we just calculated. And because we're going between grams and molecules, I need to make one more step and use Avogadro's number. Units cancel. We're just left with atoms. And again, go through and calculate. So 45 divided by 60.06, and we're going to multiply that by 6.02 times 10 to the 23rd. Round to 3 sig figs, we end up with 4.51 times 10 to the 23rd. always write your chemical as well. All right. So I know that that's a lot to deal with and a lot to practice with, but it really is the culmination of all of the different things that we've been looking at really over the past couple of units. We're just kind of combining them into a chemistry form. So really make sure that you practice with those chemical equations. Make sure you practice with predicting products, balancing equations, those types of things. Also make sure that you practice with some of these conversion factors as well. Know where to start, know where to go. Make sure you look at that mole wheel as you work through and practice. That's the best thing I can tell you to do, is just practice, practice, practice with this, and you'll be great. We've got 3 more units left. We've got a solutions unit coming up. We have one over equilibrium and kinetics, that is the speed of a chemical reaction. And then lastly, we'll finish up with over acids and bases and maybe some gases if we have a little bit of time. But again, appreciate your time. Thank you so much for watching this. If you found this really helpful, really useful, leave a like, subscribe if you're interested in more chemistry content, and we will see you very soon for the next video. Bye everybody, have a great day, and happy chemistry-ing.